Welcome back, 6th graders. Today we're taking a look at our week 10 Bellwork. So I've given you some hints and clues along the way, but I know sometimes because this is a spiral review and some of these skills we haven't seen in a while, it's helpful to be able to double check your work against mine. And there may be other strategies to solve some of these problems. I'm only going to highlight a few as we go. Let's take a look at the beginning problem here. So maybe before we do that, I should remind you, Bellwork is assigned on Mondays and Tuesdays in 6th grade, and it is due on Fridays unless otherwise stated. So do be ready that you have your Bellwork kind of working on maybe 2 to 3 problems a night, so that by Friday you have it all together ready to turn in with high quality. This first problem says use order of operations to solve. Well, if you take a look at the side here, I've given you a hint that sometimes we refer to PEMDAS. So what do the different parts of PEMDAS, this acronym, help me remember? Well, someone out there shouting, please excuse my dear Aunt Sally. Yes, you may have a rude Aunt Sally, but we don't want to talk about her today. So instead, let's remember the mathematical meaning behind these letters. So the P stands for parentheses, or maybe you would think of grouping symbols. Sometimes those look more like brackets. The E reminds me to look for exponents. Sometimes an exponent of 2 or 3 is pretty common in 6th grade. We may get up to higher exponents, of course, as we move through the upper grades. The M tells me to look for multiplication, and the D says look for division. And notice that those are kind of grouped together. Oh yeah, they use grouping symbols. Those happen on the same level, so we always think about going from left to right. Next, I'm looking for addition or subtraction. So A for addition, S for subtraction, and again, those are grouped together, telling you they happen on the same level. We'll take them in order from left to right, depending on the problem. So let's go ahead and dig in. The first thing I want you to check on is P for parentheses. Do we have some? In fact, we do. We have these rounded parentheses. They're happening right about here, aren't they? 50 divided by 2. That's the first thing I'm going to do inside parentheses. So I'm counting by 2s up to 50. That would take a really long time. Or I could think about 50 cents and splitting it in half. Or I could even take 50 and split it into some number bonds. Isn't 50 the same as, say, like 40 plus 10? Oh yeah, 40 plus 10 is 50. So if I want to find half of all these numbers, I could think about dividing them all by 2. Well, I know half of 40 is 20, and I know half of 10 is 5. So if I add those together, I should be able to get half of 50, which is 25. Oh yeah, this checks out. I could go ahead and use my number bonds to help me divide a pretty big number pretty quickly. So if you think back to what your core teacher tells you, she'd tell you to cross off what you've used already. Those parentheses are now gone. If there are no more parentheses, we can check it off and start looking for the next component of our order of operations. So next we're checking for exponents. We do have exponents in this problem. If you take a look, it's not a little tiny 2 of an exponent, it's a little tiny 3. And it's sitting next to a base of 5. The big number is all about the base. Just like in the orchestra, the biggest instrument, I think in the orchestra, is the bass. It's pretty humongous anyway. So it's all about the bass, and some of you are referencing the song right now. I don't care if it helps you remember. So this base of 5 needs to be written 3 times. So over here, so that I don't ruin my awesome organization, I took a minute to write 5 to the 3rd power. It really means 5 times 5 times 5. Most popular wrong answer, 15. Don't do that, 6th graders. Take a quick minute and think what this is saying. 5 times 5 has to happen first. That gets me 25. And next I need to multiply by the extra 5. So I'm going to count by quarters, or 25s. 25, 50, 75, 100, 125. I know that 5 to the 3rd power is going to get me 125. So I'm going to encourage you to take care of that next. Oh darn, rewind. I forgot to bring everything down. Sorry. Okay. Now, I notice that my parentheses are taken care of. Oh, guess what? We should take care of exponents next. In fact, we already talked about that, didn't we? So 5 to the 3rd power gets me 25, 50, 75, 100, 125. I'm done with 5 to the 3rd power, but I need to bring everything else down, unlike last time where I forgot to do it. So behind the 125, I have a subtract 5. And in front of that, I have an add 25. Awesome. I'm really ready to continue with PEMDAS, or my order of operations. I took care of exponents. Next I'm looking for multiplication or division. Do we have any in this problem? Oh, I don't see any. So this one is all set also. I can't seem to change pen colors, but I'm really trying. Next, I'm going to look for addition or subtraction, but I need to go in order from left to right. So I want to make sure that with addition and subtraction, they happen on the same level. So let's go ahead and add first. Mrs. Gronsky, your core teacher, would probably draw a funnel around these two numbers. I'm not good at that funnel idea, so you could just draw a little inverted arrow, or we could even just take a minute and draw kind of a grouping symbol like I've done. 25 plus 125. Oh, that reminds me of money. If I have $1.25 and I get 25 cents more, I'm going to have $1.50. I need to remember to bring down everything I haven't used yet and maybe cross off what has been used up. So I'm going to cross off that addition that we took care of and bring down the subtraction next. The last thing I have to do is subtract here. So 150, take away 5. You might want to stack it up. You might be able to think about counting backwards by 5 on a number line. So if I was at 150 way out here, and I moved backwards just 5, or what if I moved backwards 10? I'd be at 140. I only want to move backwards half of that. What number's in between 140 and 150? Oh, that's right, 145. So thinking about a number line sometimes helps me to arrive at an answer without having to do all that regrouping. 145 is my final answer. If you notice, we just made some pizza. Okay, we just made some organized order of operation work. Sometimes Mrs. Schumann calls that pizza. It's just a funny way to remember that my organization should continue to get smaller and smaller until I get down to the pepperoni. Let's take a look at the next number. If you notice, it says find the difference. Well, what does difference tell me to do? Peeking at the problem, I think it's hinting at subtraction, which is really awesome because I know how to subtract whole numbers. I do have to be careful about some regrouping if I'm using the algorithm though. Oh my gosh, it says line up decimals. Well, you know what? The decimals are lined up. And you might say, what decimals? You're losing your mind. That is very possible. But there are decimals in our whole numbers. We just don't usually see them. So where's the decimal in 256,805? Oh, the decimals are always at the back of a whole number. So if you're 12 years old, your decimal's at the back. What if you're 11? Oh, your decimal's at the back. You don't want to be 1 year and 1/10 old, right? That would be kind of weird, at least in 6th grade. So let's go with this idea. Whole numbers always get a decimal at the back. So are these decimals already aligned? Oh, they are. This decimal rule still applies, even though I didn't really need to write that today. Good. Let's go ahead and do some subtracting then. So you know with decimal subtraction, we need to bring the decimals straight down. Oh, guess what? We're going to have whole numbers. We don't usually show that decimal, do we? Oh, well, I got carried away with my hints today, so I guess we'll just go with it. Let's take a look at the ones place. I have 5 ones, take away 7 ones. Oh, -2. Ew, if you haven't learned to work with those negatives a whole lot yet. And let's not confuse our algorithm. So instead, I'll go to the nearest uh-oh, he's not home. He has nothing to share with me. So I'll go to the next neighbor. Knock, knock. Can I borrow some of your hundreds? In fact, I just need 1. Sure thing. We'll leave him with 7 hundreds. And we take his 100 and we break it into 10 little 10s. Well, that's great. We left those on the neighbor's porch apparently because he's not even home. And I really need more 1s over here. So let's take from this group of 10 10s, leave him with 9 10s, and let's regroup in the 1s place. I just took a group of 10, I break it into 10 little parts. 10 plus 5 gets me 15. And I kind of wish I hadn't done this whole decimal thing. It's taking up a lot of room. I have 15 1s, take away 7 1s. Well, 7 and 7 is 14. That's close. So 7 and 8 should be 15. I'd be left with 8. Next, I have 9 10s, take away 6 10s. Well, this is perfect. Even though my neighbor wasn't home, he had 9 10s to work with. We take away 6 of them. We're left with 3. Next, I move to the hundreds place. 7 hundreds, take away 6 of them. You have 100 remaining. And now I move to the thousands place. 6 thousands, take away 6 thousands. Well, I won't have anything left in the thousands place. Let's move to the 10,000s place. 5 10,000s minus 3, subtract 3 10,000s will leave me with 2. 2 in the 10,000s place, or 2 10,000s. Next, I'm going to take a look at the 100,000s place. 200,000, take away 100,000. That leaves me with just 1 in the 100,000s place. This could be a final answer. It's a little difficult to read, so I would encourage you to get some commas in here to help us with the notation and the reading of the number. So we'll move over 1, 2, 3 places and place our comma. And 1, 2, 3, oh, we don't need any more commas. Final answer here would probably look more like this, minus the decimal. And how do we read it? Hopefully you're thinking to yourself, well, we just talked about place values, So I'm starting way out here. This is called the hundred thousandths place. So I have 120,000, I say when I get to that comma, 138. 120,138, final answer. There's a way to check this. We talked about that on an earlier Bellwork. You could take your result, your difference, and you could, instead of subtracting, add it to this number that we took away. So we're doing the opposite or the inverse, and I should end up with the original result. So if you're in doubt at some point, that would be a great way of checking. Let's take a look at the third problem. It says find the quotient. Hint, multiply by the reciprocal, or freeze, change, flip. Oh, I don't really love this hint. In fact, my students like to confuse freeze, change, flip. They're not sure which one is the flip and which one is the freeze, and they get flipped around all day. So my suggestion would be change that. Let's talk about KCF, keep, change, flip. We could multiply by the reciprocal or keep, change, flip. Notice I didn't mention making a model. That's probably because if I did, I'd have to draw 55 little tiny units or parts in each bar. That'd be pretty confusing or tricky to count. So for that reason, I'm going to try this reciprocal approach. Well, it says keep, change, flip. Keep happens first. We keep the fraction we're given. The original fraction stays the same. We change. We're looking for an inverse here. So the opposite of division is multiplication. Next it tells us to flip or give the reciprocal. So the reciprocal of 3/5 means that the number switch position is 5/3. I'm really ready to multiply across. Unless there's some cross simplifying. We mentioned cross simplifying the other day. Oh, I don't see any. I could circle them. 11 and 5, they only share a common factor of 1. 8 and 3, well, they share a common factor of 1. I guess in this case I'm going to have to multiply straight across. 8 times 5 in my numerator gets me 40. And 11 times 3 in the denominator gets me 33. 40 33rds. That is the craziest looking answer I think I've ever seen, or at least today. So what do we do when the numerator is too great for the denominator? Oh, that's like an improper fraction, isn't it? That was totally Valley Girl. Sorry, I did go to Valley. So we're going to take that 40 and divide by 33. We're going to see how many whole groups we can get out of that. How many whole groups of 33 we can make. So 33 doesn't go nicely into the 4, but it does go into the 40 one whole time. 1 times 33 gets me 33, so using my algorithm for long division here. And there's a little bit of a regroup or some subtraction, or I could count up from 33 to 40. Oh, I know that's 7 away. I should have 7 remaining. We could write this as a final answer. I don't have to go to decimal land unless I'm really inspired to do so, but I'm not sure if a denominator of 33 is going to get me a nice terminating decimal or repetition or not. So I would suggest, let's write this as a final answer. One whole group, that comes from our quotient. Next we move to our leftover pieces. I have 7 leftover pieces out of 33 possible parts. I'm trying to make groups of 33. We would read this next number as 1 and 7/33. Now it's kind of a crazy answer, and that's kind of why we decided not to do a model approach. So we're kind of pushing you away from that, and we're trying something different called the reciprocal method, or keep, change, flip. Let's move on to a long division problem. I hope that you're getting more confident with these. This is something that you are expected to already have mastered as a 6th grader, but let's be honest, these sometimes are tough. So it says today we need to find the quotient. Well, to find the quotient, what does that mean? Well, I see a long division symbol, so they're probably telling me that I'm going to get the answer to a division problem, a result of division. So I gave you some hints over here. Sometimes we say dad, mom, sister, brother, so that we remember the order. It's an acronym that kind of helps us. The other thing I could say is, oh, does McDonald's sell burgers? Of course they do. So can you do long division? Of course you can. Let's take a look. I also gave you another hint. Counting by 13s could be tricky, so I suggested we do our multiples of 13 first. 13 times 1, 13. Check your chart or think. 13 plus 13, 26, plus another 13, 39, plus another 13. Oh, it just got real. Well, 39 plus 10 would be 49, plus 3 more. 50, 51, 52. I'd get 52 there. Let's try again. I'll add another 13. Oh, 65. I'll add another 13. 78. I'll add another 30. Here we go again. There's that regrouping happening. So I'm thinking to myself, well, 70 plus 10 is 80. And I have 8 more, 88. Plus 3 more, 89, 90, 91, 91. Let's try again. I'm going to add another 13 to this. So, well, 91 plus 10 is 101, plus 3 more, 104. I'm guessing I've gone far enough, but let's just try one more time in case. So 104 plus 13 more, that sounds like 117 to me. And because I'm so close to the end of my lines here, let's try another. 117 plus 13 more. Oh, well, 117 plus 10 more is 127, plus 3 more, 128, 129, 130. All right, let's hope this will do it. If not, we can always come back and add on more multiples, because those things never end. How awesome. Using our algorithm for long division, we would say, we start here with our divisor, and we say, how many times could we take that divisor and divide it into 3? Or if I have 3, how many groups of 13 can I make? Well, no whole groups, so I'll put a 0 here saying I did try. So instead I moved to 37, 37 hundredths. Well, I could take those 37 and start splitting them into groups of 13 or into 13 equal groups. How close could I get? Well, I'm trying to find a number close to 37 without going over. Looks like 26 might work. That's the same as 13 times 1, 2, isn't it? So 2 is the number of times that 13 goes into 37. It divides in 2 times nicely. And 2 times 13 gets me 26. And if you're not sure, you can always double check down here with our multiples of 13. Let's subtract. You'll be left with 11. Well, we just took care of the division. The multiplication, and that got us at 26. The subtraction, and here's our result. Now we need to bring down. Don't want to forget brother. Dad, mom, sister, brother in our steps. So let's bring down the 8. I now have 118 divided by 13. I'm going to try to get as close as I see something really close. Take a look. This 117 would be really helpful. If I knew how many times I take 13, well, that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. It's the 9th multiple. I think that 13 should go in there 9 times. 9 times 13 should get me the 117 we just saw in our multiples list. And when you subtract, oh, that's only 1 away, isn't it? Oh, we did our division. It went in there 9 times. We multiplied 9 times 13 to get 117. We subtracted here, and we don't want to forget brother. Is there something to bring down? For sure, a 4. I now have 14 divided by 13. Well, 13 can go in there 1 whole time, can't it, without going over. 1 times 13 is 13, and when I subtract, there's 1 left. Oh, there's nothing to bring down. I don't want to forget the brother, but seriously, it looks like we're done. So how could we write this, or how would we write this as a final answer? Maybe a mixed number would make sense. I have something remaining. So I know in the elementary you got to say the bad R word. They like to say remainders, remainders, remainders. Oh dear, sorry you had to hear that. But today we're going to try to write it as a mixed number. We see a lot more of that when we get to 6th grade. So 291 comes from the quotient at the top of my long division. It's the whole number of groups I could make. But there are some leftovers. Kind of like here, there's 1 leftover student out of 13 that I was trying to put in a group. So 291 and 1/13 is the final answer. And if this were me, I would probably make my groups all the same size, 291 students for every field trip. But one of the field trips gets 1 extra. I wouldn't try to leave them out. Time to roll to the back side of our Bellwork. And if you notice, this next problem has to do with statistics. Mean, median, mode, and range. They look kind of familiar. We've talked about them recently. This is a 6th grade skill that is kind of being reinforced. And you're going to start to see some fractions and decimals when it comes to mean, median, mode, and range. But today we have some nice whole numbers. Take a look. It says find the mode. Oops, find the mode. I'm just trying to click it twice. And the median. We're trying to find 2 key things here. So I might even highlight those for us today, just because I see that I can. We have 2 parts to this problem. Take a look to the right. It says mode means the one that happens the most often. So do you see any number that repeats? Well, the 12 happens once, the 15 happens once, the 10 happens once, the 17 it only happens once, the 13 only happens once. What is going on here? Nothing happens more often than the others. There is nothing that happens the most often. Oh my gosh. That means that there is no mode. Sometimes that happens. Sometimes none of the numbers repeat more than the others. If all the numbers only occur 1 time, we can say safely there's no mode. That's kind of weird. Next it says median, and it only shows me an example. I want you to notice really carefully, what did they do with their numbers? 11, 15, 17, 17, 18, 19, 21, 21, 21. Oh my gosh, it looks like they kind of put them in some sort of an order, right? I notice that the numbers are going from smallest to largest. Oh, from least to greatest. We need to order our numbers. So let's write a reminder. Order first. It's the first thing we have to do. So what's the smallest number that you see we're working with? 10. 10 is the smallest in our set, isn't it? What's the next smallest number? Or building up, if you will. Next I see 12. And then 13. Next 15. And last 17. I want to make sure that I have 1, 2, 3, 4, 5 numbers. 1, 2, 3, 4, 5. I didn't omit anything from the set. And this is just a long list of numbers, isn't it? A set of 5 numbers that I'm just going to put commas in between, showing that I'm listing them. Just like I like cats, dogs, and guinea pigs. So a big long list of things gets a big long list of commas. Next, they did something defined as median. Do you notice that they circled only one of the numbers? Why did they do that? Think back to what it means to find the median. Oh, median means middle. I want to find the middle number after I put everything in order. So finding the middle here. Well, some of you have learned to count or to cross off the end points, right? So we get rid of the least and the greatest. And we do it again, the least and the greatest of what's remaining. And last I'm left with 13. 13 is our median today. There was something kind of critical to this problem. A couple interesting things, that there was no mode. That's interesting. But we have to remember our steps. Always order your numbers first from least to greatest, and next we look for the middle. Sometimes you will find you don't have a middle number. That didn't happen to us today. When it does, we get to find the average or the mean of the couple numbers that might show up in the middle. Interesting. For this next problem, it says order the integers from least to greatest. Hint, negatives are always smaller than positives. So I want to go from least to greatest. We have a lot of numbers here. Take a look. I have 1, 2, 3, 4, 5, 6, 7 numbers in the set. I want to make sure I use all 7. 1, 2, 3, 6, 7. It's just a way to make sure I don't miss any. Now it says negatives are always smaller, and they want me to go from least to greatest. So I'm going to talk about ascending. Ascending. That means, whoops, helps if you spell it correctly. That's a crazy G. Helps if you remember that ascending means getting higher and higher and higher. So thinking about the left side of our number line, where the negatives occur, all the way up to the right side where the positives happen. So which negative would be way to the left of my number line? Way to the left. Oh, I have a -4, a -2, or a -50, or a -33. Which one is the smallest or farthest away from 0? You might say he owes the most money. Oh, poor -50. He's the smallest number. We'll cross him off our list. Now we're moving towards the right of our number line. I still have some other negatives to take care of, so who comes next? Who owes the most money now? Oh, you might say -33 comes next. He's still far away from 0, right? But we're getting a little bit closer. Now I still have a couple more negatives, so would it be -4 or -2? Who is smaller? Oh, -4 is a lesser number. It's a smaller number. He owes more money. Oh, poor him. He owes $4. Next I have one more negative left, so I have this -2. Good, I used their hint. I took care of the negatives, didn't I? Perfect. But now what? I have 0 and some positive numbers. So I'm getting ready to cross from my negatives to my positives on my number line. Well, would I run into 0, 11, or 33 first? Quite coincidentally, I guess I said those out loud in order. 0 would kind of be my neutral partner, right? He's kind of right in the middle of my negatives and my positives. So that's where I list him in order also. And next, I wouldn't mind $11, but I'd rather have 33 because 33 is the most. We're going to show this as a list of numbers, and we wanted to double check that we included them all. I didn't cross off 33 or 0 or 11 on my list. Do I have them? 0, 11, 33? I sure do. And drawing those lines before starting also kind of helped me. A couple more problems to review today. This next one uses some terminology that we don't use a whole lot with students, and I wish they saw it more often so it wasn't quite so frightening. It says, use the distributive property to express. Hint, find the GCF of both numbers. So yeah, they don't really want me just to add those. We learned how to do that in first, second grade, not so long ago. But we actually want to try to factor this. If you notice, I give you a hint down here. This is the format we're aiming for. The distributive property really means I want to pull out the greatest common factor. I want to distribute the GCF across the other numbers. And I'll get the same result, technically, mathematically, but it's just another way of showing how those numbers happen. So I love to talk to you about my 14 alligators and my 63 jelly beans. And we're going on a trip, and I want to pack as many suitcases as I can with the same number of alligators and jelly beans in each. So I really need to figure out how many suitcases I should get ready. So I'm going to take that 14 and that 63, and I'm going to try to find the greatest common factor first. So I'm going to use something called factor trees. 14 is the same as 2 times 7, and both those numbers are prime. I'm circling them. 63, well, check your charts or think your facts. Let's see, 3 times 21, I see it on my chart. That would work. 3 is prime, 21 is not, so we have to break it down again. 2 numbers that will get me 21. Oh, that's the same as 3 times 7, isn't it? And both those numbers, if you check, are considered prime. My trees are done. With all good trees, you should chop them down. Whoa, that sounds harsh. Well, it does help me remember to put the numbers in order. So 14 is really the same as 2 times 7. And 63 is really the same as 3 times 3 times 7. Well, next I look for anything they have in common, and I notice that both numbers share a 7. Oh my gosh, I could pack 7 suitcases. There's nothing else in common. 7 is my GCF. I'm going to pack 7 suitcases. But I want to make sure each suitcase is the same, because every day I open a suitcase, I want to know what to expect. So take a look. How many times does 7 go into 14? If you don't know, you could look back at the extra factors. Oh look, there's an extra 2. There's 2 alligators in every single suitcase. Well, what about my jelly beans? I don't want to forget to pack those. And I want to make sure I have the right amount every single day. So I go back and I say, how many times does 7 go into 63? And perhaps you know that the answer is 9. Or perhaps you say, well, how many extra factors do I have here? A couple of them. 3 times 3. Oh, that's the same as 9. What I have found is that with the distribution, I could pack 7 suitcases with 2 alligators and 9 jelly beans in each. And I kind of like the story idea of having alligators and jelly beans because we all know they'd be great on a vacation. And secondly, it helps us remember that we're not just adding, we have to sort these into equal groups. This is the distributive property that they're looking for. Now you might say, did that really work? Does that really check out mathematically? It really does. Off to the side, I could add 14 plus 63, just because some of you are not convinced that I know what I'm doing. It is questionable some days. 4 plus 3 is 7, and 6 plus 1 is 7. I get 77. Well, it doesn't look like 77 at all. Would it check out? Well, if we treated this like order of operations, we would first take care of parentheses. Do you remember what 2 plus 9 is? Oh, 2 plus 9 is 11, isn't it? So I'd get 11. And next, I'd have to multiply by 7. Secretly, with the distributive property, there's multiplication happening next to the parentheses and the nearest number. So I would have to multiply 11 times 7. And in fact, cha-ching, I get 77. Well, I wouldn't really want to combine them. I don't really want to see alligators, or I don't really want to see jellygators. That's just weird. So I'm going to try to keep them separate in my suitcase. For that reason, I'm going to write it as a distributive property. 7 groups of 2 plus 9. I probably should have said 7 groups of, I think that'll work. 7 times the sum of 2 plus 9 could also be stated. Take a look at the next problem. Here we have Emma. She says the GCF of 16 and 12 is 48. The GCF is 48. Her friend Grace says the answer is 4. Grace thinks the GCF must be 4. Who is right? Hint, you have to explain your thinking. So you can do that using a T-chart or factor trees. Well, we know how to find GCFs. We actually did that on our last problem. So I'm just going to give you this hint. I think this idea of factor trees might work. Let's take the 16, let's take the 12, and let's see if we can find the GCF. Whoa. I'm trying to keep track of myself here because my students know if they find an error in my video, they get to come to me, tell me about it, and they get a prize. That was a close one. No prizes yet, guys. All right, so here I have 16 and 12. I'm going to break them into trees, and with all good trees, we get to chop them down. And the real question is, how do you find GCF? Oh, just like we did on this last problem. We circle what they have in common. So here they had a common 7. Sometimes there's more than one pair of factors. Sometimes there are multiple pairs. And if that happens, you'll just multiply to find a final answer. Do be careful. I think 48 and 4 both have something to do with those numbers, but only one of them is a greatest common factor, meaning divides nicely into both numbers. I'm going to leave you with that one to think about. Again, I'd start with a factor tree and look for some factor pairs. For the last problem, we're reviewing coordinate plane. It's been a while since this has been introduced. And it says we want to draw and identify the polygon with given vertices in the coordinate plane. So I'm going to try to plot 3 different points using their coordinate pairs. So here it says point A is at 0, 0. Well, that means that I'd start here at the origin and I move 0 to the right or left. Oh, can't move. And 0 up or down. So I'm going to plot point A right here at the origin. I'm also going to mention this to you, and I forgot to do that here. I like to think of this with the first number always telling me right or left, and the second number always telling me up or down. I know that when you're in class right now, your teacher is telling you something different. She's showing you just another, it still works the same way, I have to point out, but she's telling you to think about whether the first number is positive or negative. Positive numbers go right, negative numbers go left. Next, she says, think about the second number. Positive numbers go up and negative numbers go down. So she has you think of it with these symbols. I want you to try to think about it with these symbols just because it's a little bit simplified sometimes. That might help. So again, I could not move left or right. It says move left or right 0. Okay, I notice you're not moving. Next it says move up or down 0. There we are at the origin. Next, we're going to look for point B. It says move -5, then 4. So -5 is the first number. Will I move left or right for -5? Well, the negatives seem to be to the left. I'm going to move to the left. I'm just going to hold my spot there while I think about that +4. The second number says to move up or down. Well, are the positives up or down from here? They're up, aren't they? So I'm going to go ahead and find that point where they intersect, and I'm going to call it point B. The last one I'm looking for here is point C, and if you notice it says I'm looking for +5, +4, both positive numbers. So I'm going to start here at the origin in +5. Would that make me move left or right for the first number? Well, positive numbers are to the right on the x-axis. Next it says +4. Is that to the left or right? Oh, I hope you say neither. This is the second number. It has nothing to do with left or right. It has to do with up or down. So +4, looks like the positives are moving up. 1, 2, 3, 4. Put a point at the intersection and we'll call it point C. We'll get it labeled. Now they did tell me to draw a polygon, so I probably would have been really wise to connect those as we went. So A connects to B and B connects to C. And you might say that's not a polygon, that's called an angle. So for a grand finale, drum roll please, we're going to connect the last point with the beginning point, and it closes in the polygon. And it gives us kind of a familiar shape. So notice that I had 3 vertices. I've made some type of a triangle. If you think about kind of word origin, tri tells you we're talking about 3, like a tricycle, 3 wheels. So this is a triangle. We might be able to say more than that, like what kind of triangle we think it is. So if I take a look at this, I notice that I moved the same distance out on both sides. I had to move -5 to the left and +5 to the right. And so that means that this y-axis is splitting it right in half. So I know a couple things. Some of you might say, hey, I know that's an isosceles triangle. If that's true, these 2 edges would be the same length. Okay? I don't think I can call it equilateral today. It looks to me like these lengths might be the same, but this length of BC looks even longer to me. Now someone else might say, hey, I think it's a right triangle. That might be true. It's hard for me to tell from my sketch if a right angle fits right here at the origin. So I'm safe to say isosceles. I might say right triangle with a question mark, because I'm not real sure if I have enough proof for that today as a 6th grader. All right, hopefully you've learned something new, reviewed something that you were wondering about. You even took a risk on this Emma and Grace question, and you found out who was right, and you gave a reason for that. So please join me next time when we take a look at our next week bell work.